guys if you want to watch it again. Here we have begrudgingly slogged our way through this list of differentiations based on our current understanding, which is a bit mixed across the class, and that's fine. But now I'm going to show you the rule. Let's start by just summarising each component here. So the constant terms, which I'm going to summarise and highlight with yellow, they are here, 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 here. They all just disappeared. They vanished. And I'll tell you why in a minute. But they just, and you guys got that in the end. You started to forget about the constant terms, which is good. When you differentiate, the constant terms vanish. You know stuff about transformations. I'll tell you a bit why now. If you get a function and you add 2 to the end, it takes that function and shifts it up 2, sorry. Yeah? Does that change the gradient of the function? Not at all. So the constant term is irrelevant to the gradient. So there's one reason why. There are others. The linear terms, I might just put an example of each. So a constant term would be like -6. A linear term would be like plus 2x. The linear terms became constant, and based on the coefficient of the term. So I'll highlight those in green. Here are some linear terms. There's a linear term, there's a linear term, there's a linear term, there's one, there's one. No, that's a lie. That is clearly not linear. Just made that up, sorry. That's not going to work, is it? I'll just take it back. There we go. There's a linear term, there's a linear term. So all those linear terms, the plus 2x just became plus 2, plus 10x just became plus 10, minus 8x just became minus 8. And then there were the other terms. So we had, in this case, we had quadratic and cubic terms. The quadratic terms, which I'll highlight in blue, and I'll leave the cubics for now. Quadratic, quadratic, quadratic. Oh, there's a linear term missing. Oops. Quadratic, quadratic, quadratic. Better fix that up, otherwise someone will complain. There we go. So the quadratic terms, like x squared, they went to a linear term, but then we also brought that squared component down, a 2 down, and the coefficient doubled. Have a look at this every time, the coefficient doubles. So when I take this quadratic term, x squared becomes 2x. Down here, 4x squared becomes 8x. Negative 2x squared becomes negative 4x. The coefficient doubles, and there's a good reason for that. And our cubic term, the coefficient tripled, although we haven't got the greatest examples of that because we've only got that x cubed. We didn't have 3 or 10x cubed or anything like that. Here is the general rule. Generally. So generally speaking, if I derive, say, ax to the power of n, and I'm going to add the notation now. D dx is one way, and there are a few, but it's one way of saying derive. You know how we write a little 2 above to say we want to square it? That's just a notational thing. It's a command. We're telling the user or the machine to square that number. Here, if you want to derive this, you write d dx. Okay, in some places you can put a little dash there. That implies, but that means other things as well. D dx is the best way, or obviously the words like find a gradient function, derive, etc. D dx of this. To determine d dx of this, the a, which is the coefficient, nothing happens to the a. It doesn't disappear because it's not a constant term, it's the coefficient of a polynomial. It just stays there and it becomes a part of the new answer. But what happens is we bring the power down, n, we multiply it by ax, and then we decrease the power by 1. That's the general rule. And you will be referring to this rule for the next year. And it will come up in your external exam. So the general rule is you get whatever it is that you're trying to derive, you bring the power down as a multiplier at the front, and then you decrease the power by 1. And that will work for any polynomial. And it's so good, I'm going to put it into an orange bubble, or an orange cloud. But if we see orange clouds, it's probably something to do with climate change. That's not good. But anyway. Any questions on that? I want to just show you linear and constant terms, and then we're going to go to some examples, okay? So just as an aside, I'll put it here as an aside, linear and constant terms are a little bit special. So if you want to do the derivative, d dx, of 7, that's a constant term, well 7 can be written in a slightly different way. It's just never written like this, but it can be. If you're going to write it as a polynomial, you might write 7 down as 7x to the power of 0. It's part of the polynomial. It's the x to the power of 0 term. And anything to the power of 0 is 1, so it's still just 7, yeah? So as part of the polynomial, x to the power of 0, and of course we bring the power down, 0 times 7x to the power of -1. Because we bring the old power down the front as a multiplier, and we decrease the power by 1. But of course 0 times anything is just 0. And there is the algebraic reason why the constant term disappears. It doesn't actually disappear, it just becomes 0. So that's one I want to show you. And d dx of 7x. I've got an affliction with 7 at the moment, I don't know why, but let's go with it. 7x can be written as d dx of 7x to the power of 1. We never put the 1 there because it's just a mathematical norm, we don't need it. If it's a 2, we put the 2 there, but if there's nothing there, we assume it's a 1. If I treat that, though, algebraically, I get this. So that wasn't meant to happen. I get 1 times 7x, and then the power drops by 1, which becomes 0, and x to the power of 0 is just 1, isn't it? Hence we get 7, which was the coefficient of the linear term. That's why we get the coefficient of the linear term. So there's my algebraic proof for constant and linear, and the rest of them follow as you'd expect. Okay? So I'm going to move on and do some examples in a second. I can see a couple of people are writing, so I'm going to give you some time to ask me questions if you have any questions, and I'll let you finish writing this down before I do a couple of examples, and then let you be. So there's no questions, people are still writing down, which means if you're watching this video, you might be wondering why there's this silence. Should I talk through the silence or just leave it be? Talk through the silence? Okay, cool. I'll just make some general comments about things. So at the moment I can only see one person writing actually, so no pressure on that person. Okay, I'm going to do 2 examples and then I'm literally going to let you be until we get into the double on Wednesday. So here are the 2 examples. They're pretty easy examples. I only need you to be able to do the 2 pretty easy examples. Just hold on a second for me. And I'll run through them now. So if I was doing example A, and it says use the rule to determine the derivative. So it doesn't say d dx, it's saying determine the derivative, so it means the same thing, it's just in words. I want to find f dash of x. That's the usual way to write the derivative if I've got my function in terms of f of x. F dash of x will be equal to 4 times 3x, and I'm going to add this little notation just in case you need it. You shouldn't need it, and you eventually won't need it, but you could write this down as 4 minus, not 3, minus 1. You know, we take 1 away from the power. I'm sure that you can all subtract 1 without having to write that down. Later on, though, we might get powers of like 1.6. Or you might get a power of x to the power of root 2, and you have to write root 2 minus 1. So that could be helpful, potentially. At some point, it's not very helpful now. This is pretty easy. I get 12x cubed. So the gradient function of 3x to the power 4 is 12x cubed. Done. And question B is slightly harder. I could write that down as y dash, or I can write it down as dy dx. At this stage, it doesn't matter. And I get 6 times 1/3 x to the power of 5, because 6 minus 1 is 5, and 6 times 1/3 is just 2. 2x to the power of 5. And that's it. That is differentiation by rule. And of course, had you have done that by first principles, it would have taken you half a page.